All right. So to solve this problem using law of conservation of momentum, I'm going to suggest that you draw a simple before and after diagram. They have a diagram, but I'm going to show you something else. So first of all, the labs you did collision and explosion lab. First of all, ask yourself which category would this fall into. Anytime two things are at rest and then they move off in two opposite directions, then that's kind of like your explosion lab, right? That example could be some astronaut in outer space, and let's say that the astronaut, because if you don't have anything to stand on, if you were in deep space and you wanted to move in a certain direction, then if you have something that you can give up, toss away, maybe a camera or something, the way you would do it is you would throw it in the direction opposite to where you want to move. So you throw it in one direction, then you move in the opposite direction with an equal and opposite momentum. That doesn't mean you're going to move as fast because it depends on how the astronaut's mass is going to compare. If anybody's seen the movie Gravity with Sandra Bullock, that's actually a really good movie with a lot of basic physics we're doing. There's quite a bit of stuff in there. So if you get a chance, just kind of watch it. After you do this, you might be able to appreciate certain things. In one scene, the astronaut Sandra Bullock, she gets away from her spaceship and she needs to get back to the space capsule. So now she's in space, she's stranded, she does, she wants to get back, and I can't remember what she had, whether it was a camera or backpack or something like that. She tossed it in one direction, which was opposite to where the spaceship was, and then she was able to get an equal and opposite momentum. That's the example of the sort of stuff you did in the explosion lab, where two things are together, one thing gets pushed in one direction, the other one goes off in the other direction. So the same goes with a rifle. So before the rifle is fired, here's my horrible diagram of the rifle with the bullet. It's not moving, right? There's no momentum before. Afterwards, after the bullet is fired, the bullet moves off in this direction and the rifle recoils in that direction. Let's label it. M1, remember we used M1 and M2? It doesn't matter which one you call 1. So I'm just going to call the rifle M1. And we are told that the rifle has 5 kg mass. So just put it on top of that in your diagram. And then the velocity of the rifle is what you're interested in calculating. So M1 and V1, as long as the ones go together. But since this is after the collision, we were using prime, so I'll just keep that here. That little, this thing here, symbol called the prime. That just means after it was fired. That's the velocity. That's what we're calculating. Calculate the recoil velocity of the rifle, so that equals question mark. For the bullet, I'm going to call the bullet mass 2. We're told that the bullet is 0.02 kilograms. And then the bullet is moving rightwards with the speed V2 prime, because it's after being shot, at 620 meters per second. So we're going to, using this information and using law of conservation of momentum, we can actually figure out the recoil speed of the rifle, actually recoil velocity of the rifle. So law of conservation of momentum tells us this. The basic statement is that the momentum before the process, in this case before firing, equals or let's say total momentum. Total momentum before firing equals total momentum after firing. Now set up your equation. Before firing, what's the momentum? Anyone? Here's the rifle, the bullet. They're both just chilling, not going anywhere. Huh? 0. Yep. So 0. These type of problems are easy. The explosion problems are the easiest ones because one side is just 0. The other side, let's calculate the total momentum. Let's set it up. What's the momentum of the rifle? That's the mass of the rifle times the velocity of the rifle. So mass of the rifle is 5 times velocity of the rifle is V1 prime plus the momentum of the bullet is the mass m2 times v2 prime, right? M2 is 0.02 times 620. Is everybody clear what I did? This was that equation I gave you yesterday, which said m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. It's always a good idea just to set it up from scratch like that, because some problems you'll see that the form will be a little bit different, as you will see in a minute. So now we need to solve for v1 prime. So do one or two more steps. So first, multiply this out to get 12 point, I think something. That's 12.4. Then subtract 12.4 from both sides. Sorry, I meant to put it here. That cancels this. And our equation now, I'll just put it on the side here, is 5v1 prime. And I'm also flipping my formula around, which is negative 12.4. And then you want to divide out 5. Divide both sides by 5. So you get, create a little more room. So v1 prime is 2.48 or negative 2.48 meters per second. You can round it to 2.5 if you like. The negative means that the recoil was to the left, right? A negative velocity means a leftward velocity. So, the prime just reminds us that this is after the process. Like, so if the whole thing was about before, as we'll see in a minute, then you just call it v1. Okay, just to differentiate the two. So after the recoil, or after being shot, the recoil velocity is that. Notice that this velocity is much smaller than the bullet's velocity, right? Even though the momentum is equal and opposite, the bigger mass is going to have a smaller velocity, right? Otherwise, it would be trouble. Like if we had actually equal and opposite velocities, then somebody firing a gun would get fired himself, like his shoulder would just be, and it would be a bigger disaster because the rifle is obviously also bigger, and the same velocity would do a lot of damage. Anyways, you see law of conservation of momentum in action quite a bit in outer space, problems involving outer space or recoil. Or there's one problem where cannon is fired. And again, that's another example of the explosion, where when the cannon fires a cannonball, at first they're sitting together at rest. That's one of the problems. And then the cannonball moves in one direction, the cannon recoils, as you might have seen in some of those older movies where they show, we don't see cannon balls being fired this day and age, but there you can see. But if you've ever seen somebody use a rocket launcher, sometimes they'll show on TV or whatever, you see that there is always that recoil associated with it. All right, let's try another example. Let me first shrink this. Oops, I need to do that, just in case if anybody didn't catch the whole thing. So here you go. Here's my problem. If you missed anything, also feel free to take a screenshot if you like as well. But that's how we're going to set it up. Draw the before-after diagram. Underneath it, put the masses and the velocities for each, for that situation. And then set up the momentum, law of conservation of momentum equation. All right, the second example we're going to do together is where it's a collision rather than an explosion. It's the type of thing that you did in like first two labs. Yeah, Cooper, you have a question?
Yeah, I went ahead and did some of this because I thought like these first two for yesterday. And I didn't draw the before and after. Do you want me to go ahead and add that on both of them?
No. I mean, you can do it without drawing those diagrams too. If you know how to do it, this is just a helpful, way of doing things.
Okay, just want to make sure.
There are many ways of doing this. Yeah. All right, let's do it for example 2. In this case, there are two balls, a 6 kilogram and a 4 kilogram ball. They're initially moving towards each other, collide head on. And then the 6 kg one is moving at 3 meters per second. The 4 kg is moving at -2. So that means equal, it's moving leftwards. So let's draw the before diagram. The before and the after. Some people like the visual, it helps them. But if you can do without the diagram, that's fine as well. You can just make a list of M1, M2, V1, V2 like that too. All right, so here's the first ball. I'm going to call this number 1 and number 2. This one is moving this way, and its mass, I'm going to call this M1, obviously. M1 is 6 kg. And its velocity is given, V1. V1 is 3 meters per second, because it's initially moving with that. M2 is 4 kg, which has an initial velocity, V2. See, I don't have a prime now in any of those, because that means these are initial velocities. After the collision, it says, after the collision, the 4 kg ball rebounds with a velocity of 4 meters per second. So this number 1 here rebounds, number 2 rebounds at 4 meters per second. That's still the same mass. You don't have to repeat this, but I'm just going to write it down because some people find that helpful. V2 prime is 4 meters. It's a positive 4, which means it rebounded to the right. And then it says, what is the velocity of the 6 kg? So M1, which is 6 kg, we are interested in calculating V1 prime. So now that we have it set up, the law of conservation of momentum says that the total momentum before the collision, which is this times this plus that times that, should equal this times this plus that times that, right? The total momentum on the before should equal the total momentum after the collision. So let's write it out. So total momentum before M1, and again, I'm kind of working on this equation. What I just said means the same thing as this. I'll just write it since I'm initially doing this. I mean, like and some people might find this helpful. That is what I just said. So let's do that. M1 times V1 is 6 times 3. It's 18. Is that okay if I just skip that step and just do that? And then this thing here, that's this thing. 4 times -2, -8, equals 6 times the question mark. Don't put a question mark. Put that as V1 prime, which is what we're looking for, plus M2 times V2 prime. 4 times 4 is 16. Let me pause. Is everybody clear how I got to that step? I just multiplied the masses and the velocities. This times this, that times that goes down there. Let me know if that's confusing. Okay, now we're going to do the algebra. 18 minus 8 gives us 10 equals 6V1 prime plus 16. In the next step, what do we do? Which algebraic step do we do next? So 6 times V1, they are together, right? So we want to first get rid of the 16. These are together, so let's subtract 16 from both sides. Now we've got, and I'll do the rest on this side, and I'm going to flip the equation to write it as 6V1 prime equals 10 minus 16, which is -6. Now I want to get rid of this 6 here, so I just divide that by 6, divide by 6 on both sides. and V1 prime is -1 meter per second. So this other, the 6 kilogram ball, moves to the left. That negative means move to the left at 1 meter per second. If you, let's say you were in a test or even for homework, and if you wanted to check your answer, how will you check your answer? Plug this -1 in here and add these two. Do 6 times -1 plus this times that. You will get the exact same total momentum on the right side as you will on the left side if you did 6 times 3 plus 4 times -2. You will see that both sides will have the same total momentum. So you can check your answer in case you're not sure if you made a mistake in your algebra. You can check your final answer by plugging it in to the right side. All right, any questions? Here you go. I'm going to shrink that so you can take a photo if you like, the screenshot. But make sure you do those examples on your worksheet as extra practice. Now you guys are ready to do, so I'll tell you what, today, let's aim at finishing 4 problems, not counting the ones I did. I'm going to give you the answers. There are a few things to look out for. So these 4, 1, 2, 3, 4. The things you want to look out for, first of all, is question 3 and 4. In 3, there's an arrow that's shot. This one, I'm definitely going to recommend just draw a diagram to kind of picture what's going on. I think it'll help you. Notice that the arrow's mass is in grams. Convert that to kilograms. Remember, when you go from gram to kilogram, you divide by 1,000. There are 1,000 grams in 1 kilogram. You need to do the same in number 4. You need to convert the units, convert these units to kg. The other thing is, in the 4th one, you also need a little bit of stuff from last semester. It tells you, this is actually an interesting method which shows you how you can calculate the muzzle velocity of a bullet in number 4. Muzzle velocity means the velocity at which a bullet comes out of a gun. You can actually use law of conservation of momentum to figure it out. If you have some sort of a detector, most of the speed detectors or velocity detectors, they'll work with an extended object. The bullet moves so fast that it might be difficult. So what they're doing in that case is they fire a bullet and it hits a wooden block. That's your before diagram. Afterwards, the bullet gets embedded in the block and they together move off with a joint velocity. So they tell you that after the bullet hit the block, it moved 0.8 meters in 0.4 seconds. Use that information to calculate your V prime using delta x over t. Remember, displacement over time, velocity is displacement over time. Use that to calculate the velocity of using this information. When you get to it, you'll know. Just right now, just make a note of that or take a photo or screenshot. And go ahead and get started. I'm going to put the answers on the whiteboard in a second. So don't leave Zoom if you're in class. I'm going to put those answers to the first 4 problems so you can check. And I can help you if you're stuck in class. All right. So our target is to finish first 4 problems. Any questions for now? All right. I'll put the answers. You need to show me all your work. Yeah, he's fine. Oh, what did I do here? I think I put the wrong answers. Sorry. Wrong answers. All right, so these are the answers to 4 problems. Just take a screenshot for now, but don't work your way back from the answers, all right? So do the problems, then check. And don't forget to convert the units for both these problems, 3 and 4, from grams to kilograms. All right. Now those of you in class,